The hypotheses are pretty simple for ANOVA. They're pretty much the same. So the null is that all the means are equal, and you can write this out with the population mean symbol of mu. So we have mu1 equals mu2 equals mu3, and that would be the case for ANOVA when there's 3 groups, but you could have more than 3 groups. So you just tack on more mu's for however many groups you have. So if you had 4 groups, you say mu1 equals mu2, which equals mu3, which equals mu4. Then the research hypothesis has to be written in words, and that's because there's a lot of possibilities that could happen, and we're saying it's one of these possibilities. So we say at least one of the means is different. And this could mean a lot of things. It could mean that mu1 is different than mu2 and 3 if you had 3 groups, or 2 is a different one, or 3 is a different one, or they're all different from each other. So there's a lot of possibilities, so you can't really write it out in like equation form with the mu's. You just kind of have to like write it out in words. So it's always going to be that at least one of the means is different. So your conclusion statement is going to be based on your p-value that you get from an F statistic. And you get your F statistic, and then you're going to calculate a p-value like you did with a t-test. Very similar. And then you're going to see if it's less than your alpha level. And if it is, then you say there is statistically significant evidence to conclude that the population means are different. So again, we're doing the same thing as in the t-test, but now our research hypothesis is different. And our research hypothesis is that the population means are different. So that's what we write here. Now, when you do a real problem, you want to be more specific. You want to say what your population means are, what you're talking about. Now, if you have a significant F-test, then you would have to do follow-up t-test or confidence intervals. And you have to control for what's called the family-wise alpha level. So let's say you have 3 groups, then you're going to do 3 comparisons. You want to know if 1 is different than 2. You want to know if 1's different than 3, and you want to know if 2's different than 3. Now, if you do that alpha level of 0.05 for each of them, and you do a confidence interval or a t-test for each of them, your alpha level, your family-wise alpha level is not going to be 0.05. It's going to be inflated. So you have to control for that. You can't just do regular t-test or confidence intervals for them. You have to fix the alpha level. So remember that alpha level is the probability of a type 1 error, so basically a false positive. So saying that there is a difference when there really is not. So if you have your alpha level of 0.05 and you really have random sampling and all your assumptions are met, then 5% of the time you're going to say that there's a difference when there really is not a difference. And you don't want to inflate that to say 0.15, right? 15%. That would be too much. So you have to control for it. There's different ways. Here are some of the ways. So you can do a Bonferroni correction, Tukey correction, or least square difference correction. The easiest one to explain is the Bonferroni. And basically what the Bonferroni does is takes your alpha level and divides by the number of comparisons you're doing. So we're going to do 3 comparisons in this example. So you're going to do 0.05 divided by 3, and that equals 0.017, or about that. And so you could do t-test or confidence intervals with your alpha level of 0.017 for each of them. And if you do that, then your family-wise alpha level will be 0.05. And so you'll keep it at the level that you want it to be. The other ones are a little bit more complicated. I'm not going to go into detail about them, but different programs will do it for you, like SPSS or SAS or R will do these for you. And then if your p-value is greater than your alpha level, then you just basically say the same thing, besides you say there is not enough evidence. So pretty much like your t-test, but there's a little bit of difference. So we're going to use an F statistic, and our research hypothesis is going to be different, so our conclusion statement is going to be a little different. And if we have a significant F statistic, then you have to do follow-up test, because you want to know where that difference is. We don't really know what that difference is just from the F statistic. It's an overall test, an ominous test. Okay?